Okay, wonderful. So Ferrol is a senior software architect at NVIDIA. He received his PhD from Tennessee Tech in 2015 and will present about their work titled Unified Collective Communication, UCC, a unified library for CPU, GPU, and DPU collectives. You are free to start whenever you're ready.
Thank you for the introduction. Yeah, so I'm just going to talk about UCC and show and kind of talk about our paper. So as an overview of this talk, I'll talk about motivation first, kind of motivating the UCC design, then go into the design of UCC, some experimental evaluation, and then conclusions. So as motivation, if we think about it, collective operations are fundamental to various workloads, especially in HPC workloads where you have multiple processes working together collaboratively to solve complex problems, typically using collectives to exchange data or provide synchronization between steps. And then also DL workloads, so deep learning workloads, where we'll have numerous processes working together to train models utilizing methods such as model parallelism and data parallelism, and collective operations enabling those parallelism features. So taking that idea and just looking at the programming models and DL frameworks that enable these applications for HPC and DL, you can see that there's a rich set of collective operations that are supported. Think, for instance, MPI or OpenSHMEM or PGAS program models like UPC, and just the subset shown on the slide here, like all reduce collective operations, broadcast, scatter, gather, all gather, and all to all. And that's not an exhaustive list in MPI, but just showing you an example. And in PyTorch and TensorFlow for DL frameworks, there's also a set of interfaces for collective operations. So this kind of shows how fundamental collective operations are to different workloads. And as we've moved into a more heterogeneous computing scenario with HPC and DL, we have collectives in CPU-based collectives over DRAM, data in DRAM. We have GPU-based collectives with data in high bandwidth memory. We even have collectives being able to be offloaded to a SmartNIC or a DPU. So there's a wide range of hardware that needs to be supported and collective algorithms that can be used. And so this motivates kind of the need for a unified component-based library. And if we have such a library, then we can provide reduced research, maintenance, and development costs for users, provide effective usage of hardware collectives, performing collectives over different hardware components and also in the network. And then provide a platform where researchers can innovate on algorithms and not just their algorithms. For example, using this unified collective library, we would be able to allow the researchers to focus specifically on their algorithms and less on the collective algorithms that are being used, but also allow researchers to innovate and develop new collective algorithms and then integrate that with a larger collective library. So keeping all those in mind, we had 5 design goals that we focused on while designing UCC. The first was, a unified collective library for HPC and DL ML workloads. And one of the main ideas there is if we unify that collective library, not only are we supporting those workloads, but we're also taking in the research that's been done over the past 20, 30 years over collective algorithms, and then we can apply all that knowledge to DL and ML workloads as well. Provide a unified collective library for hardware and software transports. So users already have the ability to have software-based collectives or hardware-based collectives on GPUs or in the NIC, on the network, I mean. Provide support for parallelism and computation communication overlap. Provide support for the GPU, CPU, and DPU-based collectives. And then, importantly, modularity and extensibility, keeping this as a component-based library that is very optimized at each different component and extensible so we can add components as new transports come out. or are needed. And so the design principles that we have for UCC, essentially everything that's a basic resource or capability of the UCC library is an abstraction. So we'll have abstractions, which are those capabilities, and these abstractions will have properties, which are the semantics of the abstractions. And then we'll also have operations, which provide interfaces to perform actions on the abstractions. These principles are applied to each of our UCC core components that you see on the right. So the UCC library, the UCC communication context, UCC team, UCC collective operations, UCC execution engine. And I'll talk about each of these components briefly. Typically, I'll have the APIs on the right. We can kind of ignore them, but I'll just try to talk about the properties themselves. So the UCC library is the object that encapsulates the resources that are necessary to have any of the other core components function. So there's initialization and finalization routines. So you initialize the UCC library, then you can perform operations on the UCC library or create communication contexts, teams, etc. And the idea is that you first initialize the library, perform your operations, and then finalize the library. Parameters of the library allow users to define the different thread models they want to support or have their UCC collective library support at runtime. So single-threaded or multi-threaded, allow the user to specify different collective types that they want the library to support, reduction types as well, and then synchronization types, which I'll talk about in a moment. Those synchronization types will define how you synchronize on collectives. A UCC communication context. So this is an object that encapsulates all the local resources necessary to perform any of the network operations. So being able to communicate between processes. The local resources might be injection queues or network endpoints. And with the communication context, we can specify affinity to a core, a socket, or accelerator, allow processes to have multiple contexts, like a single MPI process can be a part of multiple communication contexts. So you can try to leverage more bandwidth on the network, or you can have threads being a part of multiple contexts and tasks as well. But we also allow resource sharing or controls over resource sharing. So you can have that shared team idea, say, for example, with MPI or threads up above, where you're sharing a multiple context across different teams, or you can have an exclusive context where you have a single team with a single context. So it has more control of the resources. And to create a context, we have the API at the bottom there, UCC context create. So after we've initialized our library and we have our communication context, there's UCC teams. So communication context is the networking resources. Teams is the encapsulation of resources required for group operations. This is kind of your set of processes or ranks that you want to be involved in a collective operation. And there's certain properties with the UCC team. So the synchronization model, defining how the collective operations will synchronize. On entry of a collective, on exit of a collective, or on both, or even on none, so no synchronization model being used. There's ordering, where the user can specify that collectives must be invoked in the same order, or they can be invoked in different orders. For example, same order might be for something like MPI. Well, TensorFlow and persistent collectives might be invoked in different orders. And you can create a team in a non-blocking fashion, but only create one team at a time with this being a collective operation. UCC collective operations. So all collectives in UCC are non-blocking. So the user has the ability to initialize a collective. This is a local operation that initializes the information necessary for the collective operation to proceed. Then the user can post the collective operation, test the collective operation for completion, and then finalize the collective operation on completion. By having the collective operations be non-blocking, this gives you the building blocks to support non-blocking collectives, blocking collectives, persistent collectives, and split phase collectives, depending on what your programming model needs or your application needs. And on top of this, in order to support, say, for instance, applications that might have GPU compute threads, and we want to host a collective operation after the GPU computation is completed, we have an execution engine. So an execution engine is an execution context that supports event-driven network execution on CUDA streams, GPU threads, or DPU threads. And events can be library-generated events, so the completion of an operation, like a collective operation, or the launch of a collective operation, or user-generated events. For example, your data computation is complete, or your data is ready to be used in a collective. And this enables triggered operations. So this is the posting of an operation on an event. So UCC supports triggered collective operations either through library-generated events or user-generated events. And I'll show an example in a second. So let's look at this example. Basically, we have a laser pointer, a UCC library thread over here on the right, app communication thread, and an app compute thread. And in this example, you can assume the library's already been initialized, communication context already been created, and a team's already been created. So we're able to launch collective operations. So the app communication thread will initialize a collective operation using UCC collective init, and then do a triggered post based on some event. And the compute thread, we're waiting on this compute thread to finish that event. So once it completes the computation, it'll post a UCC event compute complete event. This will go to the execution engine, which knows that this collective is waiting on this. This library thread is going to pull on the event queue, and then once the execution engine tells it that it can actually post a collective, it will post the collective, run the collective, and then send an event back that it's completed the collective. So this allows you to have synchronization between your UCC collective library and also hardware-based computation, say on a GPU. So the overall architecture of UCC looks similar to this, where we'll have applications or programming models, DL frameworks, running on top of UCC, going to the external API, which will then be turned into the internal API and run on the core components that we just talked about. So the communication context, the teams, etc. As well as the execution engine, which support CUDA streams and HIP streams. But these portions we haven't talked about yet. So the CL and the TL. So the CL are UCC collective layers. So these are components that essentially are responsible for orchestrating collectives or collective execution. There's 4 supported currently in UCC. A basic CL, which is a basic implementation that composes the TLs. You can think of these as transports, but it's a team layer. It composes these TLs together so that you can perform a collective algorithm on a specific TL. And a hierarchical CL, which leverages topologies to define subgroups. So subgroups being something like the processes on a node or your node leaders on a node. And then we can use these subgroups to break a collective operation into tasks, which is just a quantum of work, and apply these tasks to a schedule. So then we can have a schedule of task 1, task 2, task 3 to complete a collective operation over a subgroup at each task. Say, for instance, we're going to do an all reduce operation. where we can do a reduce, all reduce broadcast operation, where we do a reduction first on a node. So that's your first task. And then an all reduce on your node leaders, say with a sharp TL to perform a hardware collective all reduce, and then a broadcast back out from your node leader back to your processes on the node using UCP TL, sorry, to essentially complete that collective operation. But this allows for the potential for better performance because you're taking into account hierarchical collectives. There's a vendor CL. This vendor CL is a plugin CL that allows vendors to develop their own proprietary algorithms. Say they don't want to put this into UCC and push it upstream. You can develop your own CL and then load that at runtime. And then Doka UROM CL, which is a CL that's responsible for communicating with the Doka UROM runtime that would run on a DPU, allowing you to offload a collective from your host to a DPU so that you can essentially offload progress, the progress of a collective, gain potential performance during overlap of multiple collectives. Now the TLs, or the team layer, you can think of these as essentially working with a particular transport. So a CL is your orchestration of a collective, and your TL is your implementation of collective algorithms on a transport. Again, this is component based, and more TLs can be added as more transports essentially get implemented. But in the current state, we have a UCP TL. This is a TL that's written over the UCP library in UCX. This is completely software-based collectives. This has the widest range of collectives supported in UCC so that each collective will have at least a software-based component. It supports two-sided and one-sided collective algorithms for message passing and PGAS applications. There's a CUDA TL, which is intranode collectives over NVLink. Nickel TL, which is a thin layer over nickel, allowing you to use UCC to use nickel underneath to perform your collective operation. Same thing with RICL. So this is the AMD equivalent. Then there's a Sharp TL. So we have hardware-based collectives via Sharp. We can take advantage of that TL. A self TL, which is used for collectives on a single process, which not very useful in application, but useful when you're performing continuous integration. So for a CI to test, make sure everything is okay. And then a vendor TL, which is similar to a vendor CL, just for a TL. So we performed some experimental evaluation. We had multiple test beds. Iris and Thor from the High Performance Computing Advisory Council, each with a ConnectX-6 interconnect as PCI limited to 100 gigabits per second. And then Selene as well. And so for the demonstration, what we're going to try to show is an integration with programming models, showing that we've integrated UCC with programming models for OpenMPI, OpenSHMEM, and PyTorch. Well, PyTorch, I believe, is going to be in the paper, so you can read the paper for that. I don't think it's in slides. And then hardware collectives, so showing that we can use Sharp and offload to the DPU as well, and then some application results with Mini AMR and QSolver MP. So with respect to integration into programming models, these evaluations were done on Iris. So we looked at barrier and all reduce and compared that with the Tune implementation of OpenMPI. So in each graph, Tuned is in blue and UCC is in red. And as we scale up the number of PEs, so this is each node has 56 PEs. So this is one node, two nodes, all the way up to 32 nodes. For barrier, I know there's a hiccup here. That's why we're getting 3.7x improvement, but there's significant improvement just running UCC rather than Tuned, scaling up to 32 nodes. And for all reduce, again, this is, I'm sorry, with barrier, we used TL shared memory for intranode portion of the collective and the UCP TL for internodes. So we're using the hierarchical collective CL here. Same thing with all reduce. So we use the same kind of runtime. And by default in UCC, our algorithm switches all reduce at the 4 kilobyte barrier. So data size is less than 4 kilobyte, we're using a k-nomial all reduce, and beyond that, we're using an SRA k-nomial all reduce. But you can see that UCC is outperforming Tune. Particularly, this is easier to see at the larger data sizes. And if you look at the graph, Tuned is a little bit better at the smaller data sizes, and that's okay. But we get up to a 5.7x improvement, but still there's significant improvement at the larger data sizes. With hardware-based collectives and offload collectives, so we evaluated the Sharp on Selene using the OSU micro benchmarks, where we have 8 processes per node. We showed up to a 55% improvement in performance versus UCC without Sharp. So UCC without Sharp was in blue, and with Sharp was in red. And we showed a significant improvement all the way up, so up to 55%. For the DPU evaluation, we use an OpenSHMU application, which is implementing a pipeline all-to-all micro benchmark, which is similar to the OSU non-blocking all-to-all benchmark. So in the OSU non-blocking all-to-all benchmark, there's a non-blocking all-to-all, then compute, and then wait for completion. In the pipeline all-to-all micro benchmark, you post a number of non-blocking all-to-alls, compute, and then wait for completion. And we used UCC with a UROM CL. It's not a typo. There was originally UROM CL, and this became Doka UROM CL. So this was before it became Doka UROM CL. And looked at all-to-all using TL-UCP with a one-side algorithm. And we have up to a 43% improvement in performance at message sizes between 2K and 8K. But what I would argue is that we have similar performance offloading to the DPU as well as running on the host. Now, should note that this is with a pipeline of 2. So there's 2 all-to-all collectives being run at this time. When you have 2 or more and being able to offload the progress, you can have improved performance by offloading to the DPU. And for evaluation with applications, so we looked at the mini AMR proxy application. This is a representation of the adaptive mesh refinement application. So this is primarily point-to-point operations, but there's multiple all-reduce collectives in there. I believe as you increase the number of refinements, you have more all-reduce operations. So we took this application, and what we wanted to do was just run it with no modifications to the application code. So you're just changing from using MPI tuned collectives to UCC collectives. And we ran this on Iris with 2 processes per node, so 64 processes total. And we saw between a 7 and 12% improvement with unmodified code. And this isn't going to happen with every single application. It just happened to be this particular application. And then in the bottom right, we have QSolver MP, where QSolver MP is a high-performance distributed memory GPU accelerator library for dense linear systems and eigenvalue problems. Essentially, this was extended by the QSolver MP team to support UCC as a communication backend in QSolver MP 0.4.4. And so this shows what an application can do when they extend their application code to support UCC specifically. And what they did was they were able to create 2 UCC contexts, one for GPU transports using the nickel TL and CUDA TL, and then one for non-GPU transports, so use UCPTL or Sharp TL for hardware collectives. And by doing this, they're able to select the best algorithm for use at a particular time, for a particular workload. And so they were able to get up to a 4x speed up improvement with strong scaling of PZ Hevid is a common chemistry problem on H100 GPUs. Okay, so I'll try to wrap this up with a longer presentation. So we showed that the UCC library provides high performance, portability, and flexibility for various programming models and runtimes. We've provided integrations with MPI through the component within OpenMPI, particularly, and OpenSHMEM through OSHMEM and OpenMPI, and through PyTorch through the inclusion of a UCC process group in PyTorch. We've shown flexible use of hardware, so you can perform GPU-based collectives, GPU-based collectives with, say, TL Nickel or TL CUDA, and DPU-based collectives with Doka URMCL. And we've shown some performance improvements are possible in applications without modification with mini AMR. In particular, it depends on the application and the particular collectives that are being used. And we showed significant performance improvement up to 4x when you focus you tune your application to use UCC, for example, with QSolver NP. UCC is an active and open community, so there's collaborations across multiple vendors. It's not just NVIDIA, even though it looks like that from this template. Multiple people can be involved, multiple organizations. So please check out the GitHub link here in the slides for any questions on using UCC. There's a very good FAQ and guides on the wiki at the GitHub repository, and also how to join the bi-weekly calls. So that's all I have to say, I guess.
Wonderful, thank you. There are a few questions in Slack. Are you able to access the channel, or would you like me to ask them?
I'd like for you to ask. Thank you.
All right. So the first question is regarding the strong membership assumptions of the compute participants. How adversely will your approach be impacted by a 5% instantaneous drop on the team members?
I'm assuming that means the drop isn't a failure on the team members. If there's a failure on the team members,
yeah,
in theory, the collective will fail. But in theory, what you should be able to do is recreate a new team, excluding the members that failed, and depending on your network, restart the collective. And it may work, it may not work. That's the best answer I can give you right now.
Great. The next question is, how would you overcome large latency between nodes in data centers that are distant apart?
That's a good question. I believe we would need to, so I don't have a good answer for that. So my answer is that it really depends on the algorithm as to whether or not it would fail or not, like as it is right now. But to overcome such a situation, we would need to define new algorithms and define essentially the best performing algorithms for that particular network that's so distantly located. And if we're able to do that, we can update algorithms. So just add algorithms to particular TLs that can be used in this particular situation, or leverage ones that would already be better supporting for that. That answers the question.
Great, thank you. The next question is, what are the major contributions for baseline UCC to improve 3 to 5x of the performance?
I'm sorry, which one? On here?
Sissy, could you clarify which slide you're referring to?
Oh, yeah, there's no slide numbers. It's just the programming model integration, since you said 3 to 5x.
Yeah, it says 3 to 5x.
Okay. So on this slide, particularly where we're getting a lot of the performance improvement is not just using UCP. We're also using this TL right here, TL shared memory. So this is not something that's listed in the earlier part of the slides because it's not upstream, but it's part of the HPCX package. And so this is an example of what you can get if you make your own TL integrated within UCC, like say as a TL vendor. So at each node, you're able to have just the node leaders communicating via UCP. So as you scale up, you're going to have more communication over UCP, but at each node, your communication is through shared memory. So this is a possible reason for the performance improvement over tuned, which is not necessarily using, could be using UCP, but different algorithm on top.
Great. And then we have time for probably one more question. So the next question is, I'm wondering why SHMTL was not shown on your UCC collective slide, but was used in evaluation. What am I missing?
So the reason, just like I mentioned before, this is a proprietary TL that's being included in a release, the HPCX release. That's why it's not listed in the upstream set of TLs, like right here. It's because it's a proprietary TL that would fit within this vendor TL. That's why. And we're using it because this is a TL that you can get along with OpenMPI and our entire NVIDIA network stack. So this is not a TL you cannot use. This is TL you can use. This is why we included it.
Perfect. Thank you. I think we are out of time, but there is at least one additional question in Slack if you want to answer that offline.
Okay.
And that was a great talk. Thank you very much.
Thank you.